Hi everybody, this is the second video as promised, and in this video we will demonstrate another machine learning algorithm which is called hill climbing algorithm with prior information. So we are using the same prior information that we have used in the other video where we blacklisted certain relationships in between our constructs. And again, I have my expert Anna here with me, who will give us a bit of background information on the hill climbing algorithm and the code that we are using here in R. The first thing that Anna already said before we recorded, this set seed is something that everybody knows, so maybe we do not have to mention it. It is when you're using a random procedure such as bootstrapping, basically the starting point of this whole random process. So maybe we start with the coding of the algorithm, which seems to set in or kick in at run hill climbing. Anna, what do we see here in terms of the code? It looks a little bit more complicated than the other one.
Thank you, Nicole. Yes, it looks complicated, but it's not so complicated as it looks. The first thing we see is the function. Now we change the name of the algorithm. It's not anymore grow shrink. It's called bootstrength. Actually, this function allows us to run this bootstrapping, but the algorithm itself is defined here, hill climbing, right? So this is the parameter where we define the algorithm. We run, in this case, only 500 bootstraps. Of course, this can be tuned or it can be increased depending on the data set. The data set is the same data. We define the other parameters. So typically, hill climbing works by selecting the structure for which the Bayesian information criteria is the smallest, so the closest to zero.
So here we really have a different way of identifying the structure that we will later see, namely building on this metric, BIC or BIC. And this is a metric that we also know from the PLS context, because there we also use this metric, which basically indicates how good is the data predicted, or how good is the fit to the data, and it also penalizes the complexity of the model. So it has become quite popular, I would say, in recent years. And this is the score it optimizes, if I understand this correctly.
Exactly. So it will select the structure for which the BIC is the smallest. So it will run through this bootstrapping process, creating different structures, averaging these structures, and then selecting the best model for which this BIC actually is the smallest, the closest to zero.
And this is also a feature that we should highlight here, because it was confusing when Anna and I started with the project at the beginning. We are using or referring to the smallest BIC as the best in the PLS context. And in the machine learning context, especially when we use this package B and learn, there's a specific rescaling applied. And due to this rescaling, the closer to zero the value is, the better or the best is the BIC. And that is something we just have to keep in mind when we later on also evaluate the models.
Yeah, exactly. Another thing is that that we have to remember is that if we use continuous variables, then we will use the BIC for Gaussian distribution. While if we use, let's say, categorical variables, then we just mention BIC. That's the standard.
So basically, we start kind of a bootstrapping run where it's testing the different structures, and based on the BIC, then chooses the structure that has the best BIC coming out. And there's also more code that is coming in the next line, Anna, on the display of relevant arcs or relationships. What do we see here?
Yes, so once we run this algorithm, let's run it. We are able to visualize how strong are these edges that are encountered. So we can define which are the most important edges, depending on how frequently they appear in those 500 bootstraps. Right? So if we display the output of this command, we will observe the strength and the direction, where the strength is how often, let's say, the edge between BI and use appeared in all the bootstraps runs, and the direction, whether the probability relationship between that the edge goes from BI to use, and let's say not the other way around.
So this is quite interesting. So we have to imagine we do a bootstrapping, and in the bootstrapping we have one potential structure. And then we do this 500 times, and then we measure how often is in these different samples in the bootstrapping run a certain relationship between the constructs present. And the first number here, the 85, means, and we are interested in the relationships that pop up in 85% of the bootstrapping runs. And I think the 0.5, Anna, helped me out, that was the probability of...
Exactly, to display only those edges for which the probability of direction is higher than 50%.
So basically the output that you have just explained also only gives us the ones that are above these numbers. So we see no strength or direction that is below the 85% or 0.5 in the direction values. And then there comes, I think, an advanced setting that we have been using in the paper, also in terms of, or after communicating with the reviewers for our manuscript. And Anna, what is that? What is the next step that we have been using here?
Yeah, so we may decide to retain that structure for which the edges are the strongest, or at least to define which is the minimum level of strength in order to be retained in our structure. In order to do that, we need to identify which is that threshold, right? So the minimum confidence for an arc to be accepted. So we have to evaluate that threshold. So what we do here with this function, we average across all these 500 structures. We average the strength, and then we look at this minimum threshold in the output, right?
Okay, so here we see that this kind of output gives us an information of this threshold, 0.798. And that is for us the outcome of using the algorithm with 500 bootstrapping runs. And just as a comment here, when you're using different numbers of bootstrapping runs, this number can, of course, change based on these kind of random process.
Yeah.
So now that we have identified the threshold, we are using this threshold, this average number, as a threshold in the next step of the algorithm run.
Yes. So we set the significance of the threshold, and we create this average network where each edge has to have a significance of at least 0.79.
Okay.
The network is not visualized yet. We can use a particular package. As before, we will use Gravit's plot to visualize the network.
That is already the last command in running the algorithm. And what we again see on the right-hand side is the structure that is generated by means of the hill climbing algorithm, again with our blacklisted relationships. And again, it's quite close to the conceptual models that we know from the literature. The final step after having this more exploratory overview of the structures would be to understand how do these actually really relate to theoretical mechanisms, and which of the two might be the best. We have now presented two selected machine learning algorithms that we think are very simple, also for beginners to use, hill climbing and grocery. And the next step would be to understand which of these produce actually the better model. And we will jump a little bit into this evaluation in the next video.